Okay, in this module, we will talk about closed loop transfer functions where there's an input to a closed loop block diagram that arises from a process under feedback control. So this is feedback control because we have our controlled variable y. I'll label each of the variables here. And throughout this class, we will use y as the controlled variable. So this is the controlled variable. And then d, we will use that for the disturbance. And that is an input to the system. This is the disturbance variable. And GD is the transfer function that describes how the disturbance contributes to the output. So again, we can put YD star here to denote that that's the contribution to Y, the control variable, from the disturbance. So the other input to the system is the set point. So this is the set point for Y. You can imagine that this isn't always 0. So you could bump up the set point and make a set point change. And the question is, how in this closed loop setup does the controlled variable change when you change the set point? Okay, so this is an input. So I'll write this in input. This is an input. So there are two inputs here. And this is the output that we're interested in. The output. Okay. Okay, and thankfully, this disturbance variable is affecting the process, but thankfully there's another variable u, which we can manipulate that also affects the process. So this is the manipulated variable here. And then this transfer function gu, that tells us the contribution to the control variable y by the manipulated variable. So we'll call this yu star. So this comparator, so if you sort of just look at this, then you'll see y star. The output or the control variable is the sum of two contributions. One contribution from the disturbance, one contribution from the manipulated variable. And so this is a feedback control scheme because we're measuring the control variable. We're feeding it back to this comparator, comparing it to the set point. And then we're computing the error. So this error here, this is the error. So this is the error. And E, as you can see from the comparator, is the set point minus the controlled variable. So, and this is the controller here. So this is your feedback controller. And the controller takes as input the error signal, so how much y the control variable deviates from its set point. And based on the error signal, it makes a decision as to what to do with the manipulated variable in order to bring y back to its set point, right? And again, I'll put a little heart here because this is the heart of process control. This is what the engineer adds to the process to harness it. So the engineer adds the feedback controller to the process to harness it. Okay. So really, this right here, you'll recognize as the open loop diagram, which encapsulates the intrinsic process dynamics for how D and U affect Y. But we've added a controller in the mix now. And the question is, given this control law, so I guess I'll highlight this too. So this here is the control law, GC of S. Right? The control law stipulates how, based on the error signal, we adjust the manipulated variable to make Y go to its set point. So you haven't seen an example of a control law yet, but you can imagine that, yeah, it's just any ordinary transfer function, like in CHE 361. And we can design this. So that's what's wonderful about control theory, is that we can design what GC of S looks like in order to achieve the best control. So before we even think about designing GC of S, let's just keep it as a generic GC of S. And the question is, say I do propose a GC of S for you, how exactly will the controlled variable respond to certain disturbances and certain set point changes? And we mathematically need to characterize that in order to talk about what kind of designs for GC of S we can use. So this lecture is primarily a lecture about block diagram algebra. So first I want to write up here so you know closed loop transfer functions. So for example, feedback control loop. This is the feedback control loop. It's not feed forward because you see we're measuring the controlled variable. Oops. Okay, and this is a simplified feedback control loop because we don't have a control valve here and we don't have a sensor here, right? So we're pretending that the controller directly outputs the manipulated variable. So this is a simplified block diagram, and we will make this more realistic later, but it's complicated enough as it is right now. So let's do some block diagram algebra. And again, the goal is to figure out how these two inputs, the disturbance and the set point, affect y in the face of this closed loop. And that's called a closed loop transfer function because the inputs are being input to a closed loop. So first, I like to take it just one step at a time, and let's just focus on this. And I've already written an equation here for that. So I'll just copy that down here. So we know that the control variable is a sum of two contributions. One from the manipulated variable, one from the disturbance variable. Okay? So those are the intrinsic process dynamics there. But it turns out that this, y sub u, is determined by the controller. Okay? So yd is related to d though, right? So now I'm going to focus on this. And this is CHE 361 stuff. yd is gd times d star, right? Similarly, y sub u is gu times u, right? The output is the transfer function times the input. That's all this is. So this is equal to, so y sub u is gu, u star, right? Plus gd, d star. Okay, good. So now, u, however, the manipulated variable, so I'll highlight this. There's our manipulated variable. U is actually determined by the controller, right? So we can simplify this one more time. Via the control law, and I'll move this back a bit so I can write the u right underneath that. Via the control law, u star, and all I'm doing is drawing a conceptual box around here now. And it's again, CHE 361 material. The output of the controller is the controller transfer function times the input to the controller. So u star equals GC times E, right? Okay, so I'll highlight that there, right? But the error signal is related to Y, right? So we can write what the error signal is. So this error signal E, I'll draw right here. This is the error signal. E is equal to the set point minus the actual value. Okay? And so if I do a cascade of substitutions, so I take this E, put it in there, so I take this expression, put it in here, right? And then I take this expression and put it in here, right? Then what I've done is I've related this Y to this Y here, okay? And then I can finally solve for Y. So I basically do a cascade of substitutions. So basically, let me do this again. I'll say this is Y star equals, and eventually you'll be able to do this in your head, but GU times U star, but I'm not going to write U star, I'm going to write GC times E, right? GC times E, and I'm not even going to write E. Instead, I'll write Y set point. I'm doing these cascades of substitutions, a cascade of substitutions, right? So that's E. So maybe I'll underline it to make it helpful. So this is E right here. And then this whole thing, GC times E, that's U, right? So you can see we still have GU times U. Okay, so plus GD times D star. Voila. Okay. So what we've done is related Y to itself. And your head might be spinning right now, but if we bring Y collected on the left-hand side, because we really want the output in terms of the inputs. And we have two inputs here, right? We have D star and we have Y set point star. So I'll highlight these in blue because these are the inputs, okay? So inputs. And what we want is the output in terms of the inputs. So now we can collect the Y stars. So we have Y star. And we have one of them. And then I'll bring this one over here. Plus GU times GC. Right? That equals GU times GC times Y set point star plus GD D star. Okay, and we're almost done. So now we can isolate Y. So Y star, and I'll write them in terms of S now. Well, maybe not. Okay, that's too much. So the output Y star is equal to GU GC over 1 plus GU GC Y set point star plus GD over the same thing, 1 plus GU GC D star. And voila, what we have is the output. So this is the output, the controlled variable. Let me highlight this the same color. This is our controlled variable. In terms of the two inputs, the set point and the disturbance. So this is the disturbance variable. And this is the set point. So you can imagine you make a set point change and that is non-zero, right? So now we can see, and let me make another thing. I'll highlight this too. This is GC. GC is very important too. So GD, GU, we're sort of stuck with those, right? Those are the intrinsic process dynamics as part of the open loop block diagram. GC, however, is our control law. So this is a very powerful expression because now if I told you a control law, you could evaluate how exactly the control variable will respond to disturbances under that control law. And the idea is we can play with different designs of control laws now and exactly determine, given, say, a step input and disturbance, how that's going to affect Y. And we want to tune the controller so that this disturbance minimally affects Y. We want to keep Y star at 0, assuming that Y set point is 0. So this is a very powerful expression here. And let me draw a little bit of box around it. Okay, there's not room for a box, but so down here, what this is really giving us is the servo response, right? Because servo response refers to set point changes. So this is the servo response, the closed loop servo response. This here gives us the regulator response. That's a response to a disturbance. And you can imagine that you do have both of these at the same time sometimes, so you change a set point in the face of disturbances. But often this class will only steady 1, so we'll keep the set point at 0, i.e. keep Y at steady state, and then we'll look at a disturbance, or we'll assume there's no disturbance and look at a set point change. So I think this is worth writing down. So now we know how the controlled variable y will respond to disturbances and set point changes based on three things. So the first thing we'll see is GD. So we see GD here. We also see GU. And we also see GC. Okay, so based on three things, and I already told us one. Okay, so GD is how the disturbance variable affects Y. So I shouldn't say how, I'll be more specific. I'll say the dynamics of. This encapsulates the dynamics of how D, the disturbance variable, affects your controlled variable Y. Okay? GU tells us about the dynamics of how the manipulated variable U affects Y. And GC, which is the really exciting part, because we can't really change GD and GU unless we resize the tank. GC of S, however, this is the control law, and it's up to us to design. So up to us to design, and if we design it well, then we can keep, well, there's two objectives really. If we design GC well, then we can achieve good set point tracking, a good servo response, and we can also achieve good disturbance rejection, a good regulated response. Okay, and so now from this mathematical model, from the dynamics of from GC, from GD, GU, which is our dynamic model of the process. So now you can see why it's important to study CHE 361, because from the dynamic model of the process, we can glean insights into how to design GC of S for optimal control. Right? So if we have a good dynamic model for the process via this right here, we can evaluate how different control laws will perform for both set point tracking and disturbance rejection. So it's quite exciting. And what does optimal control really mean? Well, optimal control is context dependent, so I'll put quotes around that. So this is context dependent, right? And that's because people can have different objectives depending on the process, depending on the situation. But one common metric for disturbance rejection is you want to minimize the integral from 0 to infinity of y star of t minus the set point. And you square it, because if you don't square it, then the positive and negatives could cancel out, and then y could be wildly fluctuating, and you wouldn't want that to happen, so this prevents that. So you integrate this. This is the integral of the square error of y and its set point, right? And so we want this to be really small. We want to design the control law so that this is very small. So I'll draw a little picture out here so you can see it. So you can see in your quiz, though, what an example response looks like. So this is y star. right? So in the servo perspective, you might make a set point change, right? So this is your set point. Okay, so it's 0, and then all of a sudden you bump up your set point, okay? So this is your set point. Okay? So initially we have a set point of 0, meaning keep y at y bar, but then we bump up the set point. Okay, and the true value of y might look something like this. I'll use this color. So here's what it looks like. So there's some little fluctuations. And then ideally, once you bump up that set point, the controller takes action on a manipulated variable, right? So it opens a valve or something. And then y jumps up to the set point, right? But it might overshoot a bit, and then maybe it'll come down, something like that, right? And so if you're a controller, if you use a PI controller, eventually it should get to the new set point. So what the integral of the square error here is so what it's really saying is we want to minimize. I'll use red because this is going to be error. So this here, so you basically want to minimize, not exactly this area, but it's related to this area. Oh. So you want this red zone to be 0, right? And the integral square error is very small if this red area here is small. So this is the error. So actually the error of that is the integral from 0 to t. And this is an okay metric too. It's just more difficult to compute, and it doesn't penalize very large deviations. But this is what this red area is. This is another valid dt. Yeah. So the area in red is this integral here. So this is integrating the absolute error. This is a valid something that we want to minimize as well. Common metric 4, and this doesn't just apply to disturbance rejection. This applies to servo response too. Common metric for optimal control. So optimal control is minimizing this. Okay, that was a sort of side note. But yeah, the purpose of this lecture was to derive closed-loop transfer functions. And we will consider more complicated variations later. I think it's really good to start with this very simple block diagram. But I believe that as of now, with these principles of sort of starting with the control variable, walking through the block diagram, you can derive any block diagram.